The stage is yours.
Thank you, Zlatko. Well, in this talk, what I want to do is to ask the following question. What does quantum mechanics mean? Well, without further ado, let me just skip to my conclusions. Nobody knows. Thanks for coming to my talk, and I'll take questions. Well, okay, actually, I do have a few other things to add. The first is that if you read a book or an article that asks this question and that doesn't at some stage acknowledge this basic fact that we really don't know what quantum mechanics means, then I'd advise you to read it as you might say a book review. That's to say, don't imagine that the position it is giving is one that will necessarily be either right or wrong. Judge it instead by whether it seems to offer a stimulating and productive way to think about its subject. I think this at the moment is the best approach we can take to trying to answer this question of what quantum mechanics means. Now, you don't need to take my word for it that this ignorance about quantum mechanics exists, because I'm sure that many of you will know this popular quote from Richard Feynman, who said, "I think I can safely say that nobody understands quantum mechanics." And let me remind you that he actually said this in 1965, and that was the year that Feynman shared the Nobel Prize in Physics for his work on quantum mechanics. So at that point, there was probably no one alive who knew more than Feynman did about quantum mechanics. And if this is the conclusion that he reached, you might well ask what hope is there for the rest of us. But I think today there's another way to answer the question of what quantum mechanics means. You see, one would be justified in giving an answer to that question like this. This, of course, is IBM's quantum computer. And in other words, quantum mechanics must surely tell us something about the world, because we can now use it. We can use its principles to build machines like this one, which in fact Feynman himself first envisaged in the early 1980s, in which quantum objects are manipulated so as to let us do something real and useful. If quantum mechanics was not in some sense a valid description of the world, then quantum computers would not do what they're supposed to do. But as you'll see, I think that today's quantum information technologies like this tell us something else about the possible answer to the question I started by asking, because what they embody and in fact illustrate is an emerging sense among many, perhaps not all, but many of the people who ponder the meaning of quantum mechanics, that it has something to say about the fundamental rules of what information is and how it can be encoded, moved, and transformed in the world. Now, quantum mechanics has, of course, a reputation among lay people, and in fact, among many scientists, particularly those who don't make use of it, for being impossibly hard. So here's some quantum maths for you, but it's not the mathematics that's the problem, or at least it wasn't the problem for Feynman. He could do the maths just fine. The problem was that's all he could do. What he couldn't understand is what the maths meant, what it tells us about the nature of the world. Now, Feynman himself didn't seem too troubled by that. He said, we've got a theory that works. It gives amazingly accurate predictions about how stuff will behave. In fact, it's potentially the most accurate theory in science at all. So what more can you want than that, an accurate theory that works? Well, some scientists feel the same way today, but usually we do want more, because we want to know what our scientific theories tell us about what the world is like. And it wasn't clear to Feynman that quantum mechanics lets us do that, and it's still not clear today. But I want to suggest to you that we can do better than Feynman's admission of bafflement or defeat, some might say. We don't have all the answers to what quantum mechanics means, but we do have better questions. We have a clearer sense than we did in the 1960s or even in the 1980s of what's important and what is not. And I want to try to give you a sense of what those things might be. So let me start with some things that everyone knows about quantum mechanics. And when I say everyone, I believe that this audience is a diverse mixture of experts who know much more about quantum mechanics than I do, and non-experts, perhaps non-scientists, who are nevertheless interested in the subject, and everything in between. So if you didn't know any of these things yourself, don't worry. All I mean is that these are notions that you'll encounter pretty quickly the moment you start looking at what at least has been popularly written about quantum mechanics. First of all, we're told that quantum mechanics is weird. Things don't behave in the quantum world in ways that we're familiar with, and they don't quite make sense. And here are some of the ways in which they're weird. So quantum mechanics can be both waves and particles. This is called wave-particle duality. Quantum objects can be in more than one state at once, and they can be both here and there, say. This is called superposition. You can't simultaneously know exactly two properties of a quantum object. This is Heisenberg's uncertainty principle. Quantum objects can affect one another instantly over huge distances, and this is often called spooky action at a distance, and it arises from a phenomenon called entanglement. You can't exactly measure anything without disturbing it, and so the human observer can't be excluded from the theory. It becomes unavoidably subjective. Everything that can happen, or that can possibly happen, does happen. And there are two separate reasons why this claim is made. One is rooted in Feynman's work itself, which says that quantum objects take all possible paths through space. The other comes from the controversial many worlds interpretation of quantum mechanics, which says that every time a quantum system faces a choice, it takes both choices, splitting into separate worlds. Okay, now here's the thing. Quantum mechanics itself doesn't say any of these things. They are all attempts to say what quantum mechanics might mean. Some of them are misleading. Some of them, I think, are plain wrong. Others are just unproven interpretations. So I'm saying that we need to change the record when we talk about quantum mechanics. We need to stop falling back on these tired old cliches and metaphors, and to look more closely and more carefully at what quantum mechanics does and doesn't permit us to say. And the first point to realize is that there's a big difference between quantum theory, the maths and the mechanics that scientists use daily to predict stuff and to make devices like laptops and phones and indeed quantum computers. There's a difference between that and the interpretation of that theory. And this is what's so hard to grasp, because normally the interpretation of a scientific theory seems obvious from the theory itself. Newtonian mechanics, the old classical mechanics that works for everyday objects like tennis balls and spaceships, this tells us what paths objects take as forces act on them. And we don't have to ask, what do you mean by object? What do you mean by path? It's obvious. That's not so for quantum mechanics. And let me give you a glimpse of why. To predict what a quantum object will do, in place of Newton's equations of motion, scientists generally use an equation devised by Erwin Schrödinger in 1924 to describe the idea that quantum particles might act like waves. The Schrödinger equation doesn't give us a trajectory for the particle, but instead something called a wave function. And the wave function can be used to figure out where we might find the object in space. So the shape of a typical wave function in space might look something like this. So what does this mean? Well, it's often said that it means the particle is smeared out over space. And, you know, it does look that way, doesn't it, from this? But this isn't showing the density of the particle over space. This is the wave function, and it's a purely mathematical thing. And what the wave function lets us deduce is all the possible outcomes of measurements of the particle's properties, along with their relative probabilities. So to find the position where we'll observe the particle, then we simply calculate some number from the wave function at that point in space, and that gives us the probability that we will see the particle at that point. So the wave function doesn't tell us where we'll find the particle. It tells us the chance that we might find it at any particular position if we look. And this is what's so odd about quantum mechanics, because it seems to point in the wrong direction compared to other scientific theories, not down towards the system we're studying, but up towards our experience of it. It says nothing, or perhaps I should say it says nothing obvious about what the quantum system itself is like. In other words, the wave function is not a description of the quantum object. It is a prescription for what to expect when we make measurements on that object. But it's even more peculiar than this, because the wave function doesn't tell us where the particle is likely to be at any instant, which we can then verify by making measurements on it. Rather, what the wave function, the wave function tells us nothing about where the particle is until we make a measurement. Strictly speaking, we shouldn't talk about the particle at all, except in terms of measurements we might make on it. And this account of quantum mechanics is more or less the one that was given by the Danish physicist Niels Bohr and his collaborators, such as Heisenberg, and it's known today as the Copenhagen interpretation. And I'm not saying that the Copenhagen interpretation is right, but what's valuable, I think, about it is that it tells us where our confidence about the meaning of the theory has to stop. As it stands, quantum mechanics doesn't permit us to say anything with confidence about reality beyond what we can measure of it. And here's what I mean by that. One way of speaking about this measurement of a quantum particle goes like this. We say that before the measurement, a wave function is typically this broad, spread out thing. But when we make a measurement and find the particle to be in a particular place, then the wave function switches suddenly to being a sharp spike at that single place. And this is generally called collapse of the wave function. And let me just mention that, contrary to popular belief, wave function collapse was never actually a part of the Copenhagen interpretation, at least as far as Bohr expressed it. Now, the problem here is that there's absolutely no mathematical prescription in the theory itself for how this collapse happens. You just have to assume it. You have to put it in by hand. That doesn't seem very satisfactory. But wave function collapse doesn't mean that the particle goes from being smeared out to being sharply defined once we make a measurement on it. All we can say is that before the measurement was made, there were different probabilities that a measurement would reveal it in different places. Whereas after the measurement, we can say for sure that it is here and not there. It's our knowledge that has changed. And some researchers think that this, in fact, is really what quantum mechanics is. It's a theory that describes how our knowledge about the world changes when we intervene in it. And we can't deduce from that anything about what the world was really like before we had that knowledge of it. So you see, it's misleading to talk about this situation as the particle being in many places at once. The situation tells us only what the possible outcomes of a measurement will be. And it's the same with quantum superpositions. Now, it's often said of superpositions that the odd thing about quantum objects is that they can be not only in two places at once, but in two states at once. For example, quantum objects have a property called spin, and all you need to know about it for now is that for some particles, it's a property that can have two possible orientations when you measure it. The spin, you could find that the spin of the particle points up or it points down. And so this is a property that could be used to encode bits of binary information. Up could represent a 1, down could represent a 0. And that's the basis of all quantum information technologies, such as quantum computers, because it means that spins or other quantum states can act as quantum bits or qubits. But you see, spins, these quantum objects, can be not just up or down, that's to say a qubit of encoding a 1 or a 0, they can be in a superposition of up and down states. And this is a property that somehow expands the space of possible states for quantum bits and allows quantum computers to do some calculations much more quickly than classical machines. Now, I've written it like this with these odd-looking brackets to stress that this is just a formal way of writing a superposition. It's not a picture of reality. You see, although a spin qubit placed in a quantum superposition is often said to be in the two states at once, simultaneously a 1 and a 0, let's say, that's not really right. Because remember that the wave function tells us only what we can expect when we make a measurement. And so in this case, it says that a measurement on the qubit could yield a 1 or a 0. Both, in this case, are possible outcomes. And in fact, they're the only possible outcomes. But what's the qubit like before we make the measurement? Well, quantum mechanics doesn't really tell us that. Well, now you see, I'm talking not about smeared out particles or collapsing waves, but about how information can be encoded in quantum systems and how it can be read out. And this is the basis offered by quantum information technology, which isn't just a basis, the basis of these amazing new technologies like quantum computing or quantum cryptography. It's also a new way of talking about quantum mechanics itself. And potentially talking about quantum information might allow us to see past all this old style paraphernalia of wave functions and Schrodinger equations and quantum jumps, and to get to the core of what the theory really seems to be telling us. And there's an example of what I mean by that in one of the most perplexing features of quantum mechanics, which is that the outcomes of measurements or observations seem to depend on how much information we gather about the system. And this is something that's commonly illustrated by the quantum double slit experiment. So if we send water waves or light waves through two closely spaced slits, then the waves emerging from each will spread out and interfere with one another and create a pattern where they alternately reinforce or cancel each other. So for light, if you do this, you find a series of bright and dark bands on a screen that's placed behind the slits. If you do it for electrons, which according to quantum mechanics can also show these wave-like properties, then you'll find the same thing. You don't just get two images of the slits, as you would if you were firing sand grains through a mask from a sandblaster. So, as you would in the top case here, you get wavy interference. You get this interference pattern, these many bands of more or less electrons hitting the screen. And this interference persists even if the intensity of the beam is so low that you know that the electrons will be going through the slits one at a time. It's as if each electron goes through both slits at once and interferes with itself. But now, if you put a detector close to one slit, which can detect the electron and see which slit it went through, then you'll find indeed that the detector will tell you it goes through one and not the other. The detector might click or it might not. But then if you find out that information, what you find is that the electron, this interference pattern goes away and the electron behaves like a regular particle. And crucially, it's not that the detection itself is somehow disturbing the electron's motion and getting rid of this wavy behavior. It seems to be the very fact of knowing which slit it goes through that destroys the quantum-like waviness. And you can see that that's so in what's called a delayed choice experiment, where you set up a detection scheme in a clever way so that you only detect the particle's path sometime after you're sure it has passed through the slits. So then you can be sure that the detection itself isn't physically influencing the passage through the slits. Nevertheless, finding out that information will again destroy the interference pattern. The particle will behave like a particle. But if you leave the detector there and just turn it off so that you don't know which slit it went through, then the interference returns. It's as if the particles spookily know whether or not you're eavesdropping on which path they took. It's behavior like this that led Niels Bohr to assert that there's something special about measurement of quantum systems that compels a quantum object to make a choice about the properties that it has. And until we do that, or unless we do that, the property that the object has is undefined, and we simply can't talk meaningfully about it. Now, famously, that idea was at the core of the dispute that grew up between Bohr and Einstein. For Einstein, this notion that the world is somehow indeterminate until we looked seemed absurd. It seemed like the antithesis of science itself. And in 1935, Einstein and two younger colleagues, Boris Podolsky and Nathan Rosen, came up with a thought experiment which they believed showed why Bohr's view had to be wrong. Now, this experiment was later put in a slightly clearer form by the physicist David Bohm, and that's how I'll describe it here. So this is how it goes. You have a box that spits out two quantum particles that are in an entangled state. And this means that their properties are interdependent. So let's say that they have spins, which can only have two values when measured. Like I said, spin up or spin down. Okay, so if they're entangled, this means that the measurement outcomes must be correlated between the two particles. Typically, if one has a spin that points up, then the other one has to point down. We can't specify which is which, but we know for sure that they must be correlated because of the way we produce them. So then if we measure the spin on one particle and we find that it's a spin up particle, then we know that the other particle must have spin down. Okay, now this correlation in itself might seem unremarkable because you could say the same thing about two gloves. Let's say if someone sent them separately, one glove to me, one glove to you through the mail. If I open my package and I see I've got the right hand glove, then I know instantly, without even having to ask you, that you have got the left hand one. But here's the crucial thing, because according to Bohr's interpretation of quantum mechanics, the direction of the spins, unlike the handedness of those two gloves, isn't determined in advance. It isn't determined until one of us actually observes what they've got. Now, if that's so, then this so-called EPR experiment seemed to be saying that making a measurement on one particle instantaneously fixes the direction of the arrow of the spin for the other. It's as if there's some spooky communication passing between them. And this is what Einstein called spooky action at a distance. It was Erwin Schrödinger who shared Einstein's skepticism about the Copenhagen view of quantum mechanics. It was Schrödinger who named it instead entanglement. This kind of instantaneous communication or action between two objects separated in space was known to be impossible. It was forbidden by Einstein's own special theory of relativity. So Einstein argued that quantum mechanics couldn't be the whole story here. There must be some missing ingredient, which he said was some property which we now call a hidden variable that we couldn't measure, but that somehow gives definite values to these properties, the spins say, to the particles all along. The problem is that simply measuring particles like in an experiment like this, measuring two entangled particles isn't going to tell you who's right, Bohr or Einstein, because that won't reveal anything about what the particles were like before you measured them. So no one knew how to deal with this apparent EPR paradox, as it was called. And for decades, it was just brushed under the rug. But all that changed in 1964 when the Irish physicist John Bell, whose day job was as a particle physicist at CERN in Geneva, reformulated the EPR experiment in a way that suggested that it could be conducted for real. So in short, Bell's experiment involved a clever way of combining measurements made by two observers on pairs of entangled particles, where the observers themselves decided how they'd make the measurement. And the setup is actually what's sketched behind on the blackboard here with Bell, but here's maybe a clearer depiction of it. So what you do is you look at how strong the correlations between pairs of entangled particles are for different choices of how you make the measurement. And Bell showed that if the particles were either classical or were governed by Einstein's hidden variables, so that either way their properties were actually fixed all along, then the strength of the correlations that you get in many repeated experiments here, added up in a certain way, couldn't exceed a certain value. But if they were governed by quantum mechanics, as Bohr put it, and Bohr was right to say that we couldn't see anything about the properties before we measured them, then this correlation would be larger than that threshold. So these experiments were first done in the 1970s by John Clauser and Stuart Friedman at the University of California at Berkeley using laser photons as the entangled object. And they've been repeated many, many times since, then made ever more rigorous and ever more able to rule out possible loopholes in Bell's argument. Every single time they've given the same very clear result, which is that quantum mechanics alone is right. Bohr's argument seems to be right, and there's no argument for Einstein's hidden variables. So how can this be? What's wrong with the EPR argument? Well, Einstein and his colleagues made the perfectly reasonable assumption of locality, which is really saying that the properties of a particle are localized on that particle itself, and that what happens to this particle here can't affect what happens to another particle there in some different part of space without some way of transmitting an effect across the intervening space between them. But it seems that nature doesn't work that way at the quantum level. We can't regard the two particles in the EPR experiment as separate entities, even though they're separated in space. When they are quantum entangled, they have to be both considered in some sense a single non-local entity. And in fact, it's only if we accept Einstein's assumption of locality that we need to tell the story in terms of particle 1 somehow influencing the spin of particle 2 when we make the measurement, this spooky action at a distance. The alternative view is that we have to invoke quantum non-locality. This idea that somehow quantum properties can be delocalized between two or more objects. So here again, we seem to find this issue of how measurement and information and the information we get from it seem to affect the outcomes itself. As with the double slit experiment, you can show in a Bell test that it's not the physical act of making the measurement on one particle that somehow seems to fix the property of the other. It's the matter of whether that measurement unambiguously tells you what the state of your particle is. So it's the knowledge that matters. Measurement has become something of a dirty word in quantum mechanics because it seems to bring up all these peculiarities. In fact, John Bell placed it on a list of bad words, which incidentally also included information, that he thought should be banned from talking about quantum mechanics. But these days, measurement isn't quite the mystery that it once was, even though it's not fully understood yet either. You see, in Bohr's view, a measurement was necessarily something governed by classical physics, because ultimately it needed classical scale stuff, a piece of apparatus and us to look at it. And so for him, that was the end of the mystery, because he said that quantum and classical were just distinct regimes, and we shouldn't expect to be able to pronounce about what went on in the quantum world from the perspective of the classical one. In effect, he declared that there was a fundamental divide between them. Now, it's not surprising that seemed a deeply unsatisfactory answer to some researchers, including Einstein. But today we can do somewhat better than that. We know, for example, that any measurement involving the interaction of a quantum system with some classical environment, like a measuring device that aims to extract information about it, any measurement like that involves entanglement. Entanglement happens whenever one particle encounters another. In fact, quantum mechanics says if they interact, that's the only thing that can happen. They have to become entangled. And if you make a measurement so that more and more of these interactions with the environment accumulate, the quantum system itself becomes more and more entangled with its environment. You might say that what this means is that the process spreads out the quantumness of the original object into its surroundings. And in that process, the quantumness kind of gets diluted into the environment. And here's what I mean by that. Let's say you have a quantum bit, a qubit, in a superposition, and then you make a measurement on it, and it becomes entangled with its environment. So the superposition then spreads into those particles too. And if you want to demonstrate that you still have a superposition there at all, then you have to look for it in all those entangled particles. And that quickly becomes impossible. It would be a bit like trying to keep track of every single gas molecule that you just breathed out as it collides with and mixes with all of those in the air around it. So this process is a real physical process. It's called decoherence, and it leads to the apparent disappearance of quantum properties like superposition in the original quantum object when it's observed and when its properties are measured. And it's possible to calculate how fast decoherence should happen when a quantum system interacts with its environment. And we find that generally it's so fast it's almost instantaneous. So, for example, if you could somehow put a dust grain in the air in a quantum superposition of states, you can calculate that it would decohere in this room in about 10 to the minus 31 seconds, faster than anything we can measure. And what you're left with when that happens is classical behavior. Definite properties with fixed values, such as a well-defined position in space. In fact, according to one theory that describes how this decoherence changes quantum to classical, it's a theory called quantum Darwinism. This process not only gives objects fixed definite values of their properties, but it actually picks out from all the quantum features precisely those properties that are meaningful in the classical world, properties like position and speed and charge. So only certain quantum features, the theory says, have the right characteristics to survive the filtering process of decoherence. And they do that. They have those properties because they are particularly good at making many imprints or copies of themselves in their environment. That's where the Darwinism part of the theory comes in. You see, when we make an observation of an object, what we're really doing is detecting the traces that it imprints on its environment. You can only see me now because of the photons that have scattered from my particles and made their way into the camera. This all gets a bit more complicated when we're talking about virtual talks, but it sort of works. And you can only hear me because of the imprint that my particles have made on the air molecules, the movements of the air molecules. In fact, you could reconstruct everything you can say about an object, like a dust grain, say, from those imprints, like the photons of light that are bouncing off it here. You could reconstruct all of that, even if just after those photons have bounced off, the object itself was somehow to magically vanish from space. You could still see it from the imprint that it's left for a short time. And you can all agree on my properties, my position, the color of my shirt, what I'm saying, classical properties like this. You can agree on them because there are lots of the imprints that I'm making on the environment. They're highly redundant imprints. There are loads of scattered photons from me, enough for all of you to share. If one of you was somehow able to harvest every photon I scatter, no one else could see me and make any observation of me. And it's this creation of many copies or imprints via interactions and entanglement with the environment that is described by quantum Darwinism. And that in this theory, at least, that is how quantum becomes classical. Now, there seems to be no avoiding decoherence for objects the size of a dust grain. Even in a vacuum, interactions with thermal radiation, infrared photons from the warmth of the room, would still cause it to decohere in about 10 to the minus 18 seconds. Even if you put that grain of dust in the cold emptiness of interstellar space, it would still decohere in about a second because of the microwave photons out there from the cosmic background radiation. So in other words, the reason we can't generally observe quantum effects like superposition in objects of everyday scale is not because there's some law of nature that forbids quantumness at those scales, but because decoherence will destroy it almost instantly. And it does so because of quantum entanglement itself. If we could figure out how to put a tennis ball in some well-defined superposition of states and to isolate it completely from sources of decoherence, and yet, this is the tricky bit, somehow still monitor its state accurately enough, quantum mechanics says there's no reason why such a superposition should be impossible. Now, some physicists think that there might be other factors in that situation that will come into play that will destroy quantum coherence anyway. Some think that gravity will do it. But it's not clear that anything extra is needed to effectively banish quantum phenomena at everyday scales. In other words, The world is quantum all the way up. And classical physics is pretty much just what quantum physics looks like when you're 6 feet tall. And that's really what I mean by the title of my talk. And I should just add for this audience that decoherence is the enemy of quantum computing. Computing with qubits relies on keeping them in a collective state of superposition while the computation proceeds. Decoherence will mess that up. And that's why quantum circuits have to be cooled to such extremely low temperatures within a whisker of absolute zero, because this suppresses all the thermal jiggling that would otherwise disrupt the qubits. And it's the difficulty of maintaining this coherence and suppressing decoherence in ever greater numbers of entangled qubits that explains why quantum computers so far don't have more than around 70 qubits or so to play with. But it's a testament to how much power quantum rules give you that already quantum computers can do in seconds with just that number of qubits some calculations that would take today's classical supercomputers 1 billion years or so. Now, there's a curious thing about Bell's experiments that's often not remarked upon. You remember I said that the quantum mechanics allows correlations between entangled particles to be stronger than they would be in classical physics or for hidden variables. But quantum mechanics too sets a limit on how strong those correlations can be, and it's not obvious why they couldn't be stronger. We don't know why that is, why the world isn't, if you like, even more quantum than it is. But one useful way to think about what's going on there is that there seems to be a limit on how much sharing of information quantum mechanics permits between entangled particles. So here again, what makes quantum mechanics what it is seems at root to have nothing to do with mathematical notions And this is precisely where some scientists think we should start in trying to reconstruct quantum mechanics from scratch, not from these ad hoc guesses, as they really were to begin with, about waves and particles and Schrödinger equations, but from some simple axioms, some simple assumptions about what is permitted with information, how it can be encoded, how it can be transferred, how it can be read out. And I want to give you just a flavor of what this sort of reconstruction would look like. There are many of them that have been suggested. They all are somewhat similar. And I've taken one at random that was suggested in 2009 by Borovoje Dakic and Czeslaw Bruckner at the University of Vienna in Austria. They proposed what they said were 3 reasonable axioms about how the world might be. And this is what the axioms were. That first of all, the most elementary components of the world, whatever those are, can carry no more than 1 bit of information within them. They assumed, secondly, that the state of what they called locality, so the way they expressed it was the state of a composite system made of many subsystems is completely determined by measurements made on its subsystems. What that really means is that there are no secret mechanisms like hidden variables manipulating what's going on. Thirdly, they assumed that this property of reversibility, that you can convert any pure states from one to the other and back again, like a coin toss, flipping heads and tails. So Dakic and Bruckner showed that with these assumptions alone about information, really, that they will lead you inevitably to only 2 sets of possible rules about how things can happen. And those are the rules that are described by classical mechanics and by quantum mechanics. And what's more, if you modify this 3rd axiom to say that to assume that states can be interconverted gradually, little by little, rather than in one big jump, then you only get rules that conform to quantum mechanics. So for a classical coin toss, for example, a head and a tail interconvert sort of abruptly in one big jump. It's either heads or it's tails. In a quantum system, you could have a situation where, you've got your hand down on the coin and it can gradually, as you hold it down, interconvert from heads or tails without having to pick it up and flip it over. Okay. So the point is that these axioms about information can by themselves lead to quantum behavior that we're familiar with, like superpositions and entanglement. And some researchers think that these efforts at quantum reconstruction might lead to a completely different perspective on quantum theory, one in which the physical meaning of all the seemingly strange behaviors at last becomes clear. Now, it remains to be seen whether that will happen, but I think it's already illuminating that they all focus on information, on how answers or measurement outcomes are contingent on the questions we ask and how we ask them. And I think this is the most productive way to think about what quantum mechanics seems to be telling us. And it's a perspective that I think is illustrated really nicely by a metaphor that the American physicist John Wheeler, who studied under Bohr and who had Feynman as one of his students, incidentally, he suggests that maybe we should think about quantum mechanics as like this. Let's think of it as being a bit like the game of 20 questions. I'm sure you know this game. So it's the one where one player leaves the room and everyone else in the room agrees on a certain person, a historical figure, a well-known person, and then the person outside has to come back in and they start to ask each person in turn a question to try to find out who it is that they've chosen. And they have to be questions that can only be answered yes or no. So you see, they're really quantum questions. Now, imagine you're the questioner here. So you come back in, you start to ask questions and you get your answers. You start off, is the person male? And the first person says yes. And the second person, then you go to second person, is he alive? No. Okay, and you carry on. And you find an odd thing that as you go on asking more and more people, it takes them longer and longer to answer your question. It's as though, they're having to think about it. Well, that's odd because, if they've agreed on a person, it's either the answer's either yes or no. What is there to think about? Anyway, you carry on playing this game and eventually you think you're zeroing in on who it is. And finally you think, I've got it. And you say, it's Richard Feynman. And everyone laughs and tells you that you're right. It's Richard Feynman. And then you say, well, what was going on? Why were you taking so long to think about the answer? And they explain how they decided to play this. So instead of deciding on a particular person when you were out of the room, what they decided to do was to say that the answer that anyone gave to the question you asked had to be consistent with all of the answers that had been given before. They didn't decide on anyone, but the answer that they gave had to correspond to all the answers that have been given so far, had to correspond to a famous person of some sort or another. And so, of course, as the answers went on, it became harder and harder to think, well, who does that apply to? They're male, they're dead, and so on. They're a physicist, and so on. You have to think harder and harder. And what happens is that as the questions are asked, the possible answers get narrowed down. And in the end, there's only one person it can be. It has to be Richard Feynman. But everyone was forced by the nature of the questions themselves to converge on that same person. If you had asked different questions, you'd have ended up with a different person, a different answer. So the answer you got depended on the context. There never was a preordained answer. You brought that answer into being in a way that is fully consistent with the questions you asked. And what's more, the very notion of an answer at all only makes sense when you play the game. If you'd come back in and said, oh, I can't be bothered to go through this, just tell me who you chose, there would be no answer to that question. You have to do the inquiring before an answer will be forthcoming. So quantum mechanics is like this. It seems to be a theory of what is and isn't knowable and how those knowns are related. And I like to think of this in terms of a distinction between a theory of isness and a theory of ifness. Quantum mechanics doesn't tell us how a thing is, or how a quantum thing is. It tells us what, and with what calculable probability, it could be, along with a logic of the relationships between the various coulds. If this, then that. And what this means is that to truly describe the features of quantum mechanics, as far as we currently can, we should replace all the conventional isms with ifms. So, for example, we shouldn't say, here it is a particle, there it is a wave. We should say, if we measure things like this, the quantum object behaves in a manner that we associate with particles. But if we measure it like that, it behaves as if it's a wave. We shouldn't say the particle is in two states at once. We should say, if we measure it, we will detect this state with probability X and that state with probability Y. This ifness is perplexing because it's not what we've come to associate with science. We're used to science telling us how things are. And if there are ifs at all, it's because we're partially ignorant about that. But in quantum mechanics, as far as we can tell at the moment, the ifs seem to be fundamental. Well, okay, you might say, but what's the stuff that this ifness is referring to? Quantum mechanics doesn't obviously tell us much about that, and all we have right now are hints and guesses. And to try to bring them into sharper focus is a tricky business. It seems to demand an almost poetic level of expression, which will send some physicists scurrying for cover. So here, for example, is an attempt to do that the physicist Chris Fuchs suggested. He says maybe quantum mechanics is telling us that the world is sensitive to our touch. It has a kind of zing that makes it fly off in ways that were not imaginable classically. The whole structure of quantum mechanics may be nothing more than the optimal method of reasoning and processing information in the light of such a fundamental, wonderful sensitivity. And what Fuchs means here is not the mundane truism that the human observer disturbs the world. That's true in classical physics. Rather, quantum mechanics may be the machinery that we humans need, we humans pitched at a scale midway between the subatomic and the galactic, to try to compile and quantify information about a world that has this incredibly sensitive character. It embodies what we've learned about how to navigate in such a world. And I think it's vital, at any rate, that we understand that this ifness doesn't imply that the world, our home, is holding anything back from us. It's just that classical physics has primed us to expect too much from it. We've become accustomed to asking questions and getting definite answers. What color is it? How heavy is it? How fast is it moving? Forgetting the almost ludicrous amount about that we don't know about everyday objects, we figured that we could go on forever asking questions and being answered at ever finer scales. And when we discovered that we can't, we felt shortchanged by nature and we pronounced it weird. I don't think that will do anymore. Nature does its best and we need to adjust our expectations. So we need to go beyond weird. Thanks very much.
Thank you, Philip. Thank you, Phil, for the wonderful talk. And I can relay to you a few comments before I get to questions from the audience. And folks in the audience, please feel free to post questions again in the chat. The chat is very active right now, so I'll try to pull them out of the stream here. We have, by the way, a few folks I would just like to relate to you, since you can't see the chat yourself, said this is, nice stuff, enlightening and mesmerizing. So I thought I should relay that. We had quite a few discussions and questions, I think, that spawned off of the discussion as to, let's see, hopefully you can see me now. There we go. As to why is quantum weird in the sense of deterministic? Is it because we're used to deterministic theories? And I think you touched on this throughout the talk, and this is one of the essential points. But maybe if we kind of come back to that, there was the locality, the deterministic versus maybe non-causal potential. Maybe if we could sort of get your thoughts again in a bit of a summary here of the discussion that is going on in the chat.
Yeah, okay. Well, I mean, certainly, it seems to me that as far as we can say at the moment, quantum mechanics isn't deterministic. There are ways of interpreting quantum theory that are deterministic. that in fact do return us to some sort of picture of there being real particles that have real properties and real places out there. There is there are interpretations that suggest that, and if you like, all the quantumness, or what we've conventionally called the weirdness, is kind of put onto another aspect of the theory, but we recover the particles. So that's possible, but it's, you know, it's unproven, and it's just one interpretation. And at the moment, it seems to me safest to say that you know, that there does seem to be this fundamental indeterminacy in quantum mechanics, so that if we make a measurement on a system, all we can meaningfully say is what the probabilities of the outcomes will be. We can that perhaps we can never say more than that. So we can never exactly predict what we're going to find.
That's very interesting. And I think, folks, I'm sorry, we were going to have to leave the videos off, but hopefully you can still hear us just fine. We're having some bandwidth issues today. Yes, so interesting. And maybe a follow-up question from the audience here. In the classical world, you know, are we perhaps too used to trying to write down deterministic laws? You know, could the classical world be modeled under any probability or a probabilistic theory, perhaps, to rephrase the question here? And should that really be the comparison between the quantum world and the classical?
Well, I'm certainly not an expert on this, but what I can say in response to that is that these efforts at quantum reconstruction that I talked about, one way of looking at that is that really quantum mechanics is simply a kind of probability theory. It's just a different sort of probability. You know, probabilities work a bit differently from how we're used to them in the classical world. And that, you know, one way of looking at it is that you know, we should be thinking probabilistically, you know, more generally. And, you know, there are a whole set of possible probabilistic theories, or theories of probability, and one of them corresponds to quantum type rules. So you know, here again, we sort of come back to quantum mechanics being a theory about knowability and how much the world is really knowable. I mean, the way that I think about it, that makes sense to me, is to suggest that quantum mechanics seems to be telling us that it's possible for us to ask more questions than nature can have answers, can have definite answers for. That seems to me to be really the point. And that doesn't seem to be such an unreasonable thing to propose. Why should every question that we can pose, that we could pose, necessarily have a definite answer? And quantum mechanics seems to be saying it doesn't. And so you have a choice. If you choose to ask these questions, you'll get this set of responses. If you choose to ask this set of questions, you'll get a different one. And they may not be compatible with each other because you ask different questions. So it depends on the context of the questions that you're asking.
I think that's enlightening, yeah. And maybe that reminds me a bit of this game you brought up earlier, which was very nice. And I think you concluded by something along the lines of you brought that answer into being of, oh, it's Feynman, by asking that particular set of questions. And I think it was Sasha Korotkov, as a physicist, who also says, in quantum mechanics, you don't see what you get what you see. And that brings me to maybe your perspective or thoughts or opinion on knowability, right? So in these more recent experiments, the quantum trajectory type of experiments, those experiments can't always, they usually can't tell you the future, they can't predict the future, but they can always tell you exactly what, in a way, the state is, the quantum description, the quantum state is doing, as you are subjecting the system to an ongoing interrogation, a measurement. And there seems to be this very close one-to-one direct correspondence. In a sense, the randomness only comes if if you now suddenly change your measurement to something else, but you have a knowledge about the system that is conditioned on what you're measuring, and you can update that. And there's always, in the case that you can do that update perfectly, which you can get close to these days for some experiments, there are always not a complete set of questions you can answer perfectly. Like you said, there are always more questions in quantum than perhaps you can always get a deterministic answer for. But there is a subset of those questions that you can always know that if you ask the question, is the qubit along the x direction, let's say, you always get a perfect one, even though you've been injecting randomness into the system throughout with your measurement. Maybe that was a bit long of a question, so I apologize for that, Phil. But perhaps we can get your thoughts on QTT and a bit of that. That would be great.
Well, I mean, of course, Radko, you're the one who knows about this rather than me. I was absolutely fascinated by those experiments for various reasons, but I think that perhaps the main one was that it seemed to me that you were really starting to narrow it, to zero in on what is happening when we make a measurement, and in particular to dispel this idea that measurement is this mysterious black box that suddenly turns all the quantum vagueness into something concrete. What really excited me about them was that you can see that process happening, and that there are laws to it. That it's not just magical and unpredictable and everything else. That as you say, if you are able to follow it with sufficient time resolution, in sufficient detail, knowing almost everything about what is happening in the system, then you can see something that does look like a trajectory that is taking the system from one state to another. And this is why, I mean, it certainly convinced me that, this notion of wave function collapse as a mysterious thing that suddenly snaps, a wave into a particle, that we really, it's never really been needed in quantum mechanics. I understand why it got there, but it's time to get it back out again, because we don't need it. And it seems to me that that is getting, much closer to having a proper understanding of what it is that happens when we make a measurement. Perhaps the one thing, and I'd be interested, in whether you have thoughts about this, because the one thing that it doesn't seem to explain, and this is really the sort of fundamental mystery in quantum mechanics: why do you only ever get one thing? And of course there are some interpretations that say, well, you don't, you just get both in different universes. But as far as we can ever see, quantum measurements are unique. So where does that uniqueness come from, given that we know in principle more than one outcome is possible?
That's a really deep question. I think, in fact, I got asked a similar question at my dissertation defense in the private dissertation part, where they take you aside to a room and quiz you until you come to a point of anyway. So I don't know that I have a great answer, but maybe a few thoughts that are probably something you've written about quite a bit, as well as this notion you brought up earlier, and I think you said Bell maybe had introduced it, or of two different disconnected worlds: the world of the quantum and the world of the classical. And there's this notion of Heisenberg's cut, the boundary between these two, and there's no prescription in any textbook or in any paper that I know of that you can find that really pins down where does this difference occur between what you call a measurement apparatus and where you get classical results out of the system, and what is the quantum system. So, for example, coming back to the quantum jumps Nature paper you brought up earlier, you could take that Heisenberg cut at different stages of the experiment and pretend like, for instance, just the qubit itself is quantum, and it's being subjected to a particular classical measurement apparatus that has this particular type of question it's interrogating the system with, kind of like the game that you mentioned earlier. But it turns out that and what we had to do for the experiment is we moved the cut one step further. That apparatus was a particular type of superconducting cavity, and we modeled all of the quantum behavior of it as well. Now that particular cavity is then followed by another quantum amplifier, and we could actually include the quantum amplifier itself and also make this very large now quantum system. Now you have 3 different quantum systems that are all coupled together, and you have this kind of matryoshka doll of nested larger systems that are increasingly becoming more classical in a sense, because at each stage you're amplifying in a sense the signal. There's more quanta of excitation that are getting involved, and perhaps with that, once you have, like you said, the grain of dust that's floating in the air, when you have so many quanta, so many excitations, then you tend to couple more strongly to this, decoherence, right? Whatever that is precisely in itself. And you tend to move already in the limit of where a lot of the quantum nature tends to seem to get erased or washed out in a sense. At that stage, though, it's still purely quantum system. You could reverse and undo the measurement in the sense of taking that information, because you're keeping track of it, and sort of feed it back into the system. You still have all those degrees of freedom. And then after that following amplifier that comes after the cavity, then we kind of don't know where to draw that Heisenberg cut. In terms of the empirical experimental world, that's roughly as far as our models are able to get us. After that, we don't really have an equation or a model we could write down that we're currently able to say, oh, now it's quantum. So it's empirically, we see that, okay, it occurs somewhere there, but is that a limitation of our ability to express it or not?
So it's like, is this, it sounds to me as though this is, again, really about information, that in, this notion of a cut, it sounds as though what that really means is, where do you decide the point comes where you're not going to any longer, or you can't any longer gather pretty much comprehensive information about everything in the system? And once you relinquish that attempt, that's where the cut happens, because you have imperfect information. Is that the right way to look at it?
I think that is definitely a practical way to look at it. That seems to work in practice. Is it the ultimate solution? I couldn't say. Sorry, go on.
No. That's fine. That's just what occurred to me as you were describing the experiment. It seemed to be a matter of, well, how far out can you keep going in your apparatus and still retain the ability to monitor, more or less everything that is happening at the sort of quantum level.
Exactly. And we've been able to now push that further and further out, and see that as you kind of climb up the matryoshka doll, or the chain of nestedness here, you can move that Heisenberg cut quite far out, and still model things. But at the end of the day, we've simply moved the cut further away, but we still have the cut. So is it a fundamental cut or not? I think that's an open question as far as I could tell. But another way that people think about, and I think we'd mentioned this, is that you could say that to the contrary, I think, of what Bell had said. John Bell, I think you said, had banned measurement as a bad word. I think to more experimentally minded people like myself, measurement is actually probably the essence of the whole theory. It's what we do, it's what we model, it's what we describe. That should actually be the core of it. So perhaps we should start not with Schrodinger's equation, which describes what the state of the system, whatever, if that even exists in of itself out there, is, but maybe we should start with a description of the measurement. So, I could say closer along the lines of QT. You could take that interaction between what you call a system and the actual measurement, because the problem is that in Schrodinger's equation, a measurement is completely absent. So Schrodinger's equation is linear, deterministic. There's nothing really weird in Schrodinger's equation, in a sense. The randomness, if you want, the weirdness of the quantum randomness that comes into play only occurs at the stage of the actual measurement, when you have von Neumann's postulate and so on. And so it's that process that I think you so nicely pointed out is what now the field of physics is being able to kind of open the hood on and describe. But I think we've maybe said a lot on this. Perhaps if you'd like to share this, a question from the audience here on, and you'd let me know if you'd like to take this one. If you could you share your thoughts on Maxwell's demon, and perhaps how that relates to all of quantum mechanics, in the sense that you have, I'm kind of reading into the question here, you know, this when it comes to knowability and trying to kind of sift or parse and sort of beat the laws of thermodynamics in a way, but now at the level of quantum. So perhaps if you'd like to offer some thoughts on that. On Maxwell's.
Yeah. Well, very timely. I've just been writing about Maxwell's demon today, and I have done previously. And you know, everything that is discussed within the context of Maxwell's demon is classical. Although there is a quantum Maxwell's demon as well, there is a quantum version. But you know, classically, again, it illustrates how so much seems to come down to information, the question of information. So and in essence, what Maxwell's demon tells us is that information itself is a kind of resource that we can use to do stuff with, which I just find extraordinary. I mean, it may be that not everyone knows what Maxwell's demon is, so that, you know, very, very briefly, it was a way that James Clerk Maxwell in 1867 suggested of subverting the second law of thermodynamics. The second law says, you can express it in many ways. I mean, the simplest is just that heat always flows from hot to cold and never the other way around. But what it also implies is that you can never get energy for free. You can't. There's no perpetual motion. That any system that does work, it's always, some energy is always going to be wasted and lost as sort of random motions to the system, as entropy, in fact. So the entropy of the universe always increases. And Maxwell didn't like this, partly for religious reasons. And so he came up with this idea of a little demon that could actually reverse this by having a trap door between two compartments with gas in them, both with gas in them. Gas starts at the same temperature in both, but the hotter molecules are the ones that are moving faster in the gas. So the molecule, the demon looks at the molecules and sees if a fast molecule is approaching from one direction, he opens a trap door and lets it through. If a cold molecule is approaching from the other direction, he opens it and lets it through. And so all the hot ones go one way, all the cold ones go the other, and he ends up with hot gas on one side, cold gas on the other, which is basically, then there's a thermal gradient that you can tap as some sort of power source to do some useful work. So you've got energy essentially from nothing, from just an ordinary gas. So for a long time, people figured, there must be something wrong with this. How can it subvert the second law? And it turns out that the answer is it can't, because of information. And in this case, it's the information that is recorded in the demon's mind, that it has to be gathering information about those gas particles in order to do what it does. And eventually, that information, its mind is finite, and it has to erase that information. Otherwise, it's just too full and it can't do any more. And erasing that information costs energy. And in effect, you get back all the energy that you thought you'd got from the operation of a demon. So there's, you still don't get anything for free, any energy for free. So this is about information, and people have realized that actually what this means is that what looks to be sort of randomness, statistical randomness, at one level, if you can zero in and get detailed information about what is going on, then you can use that information to mine the sort of random fluctuations in there and get energy out. And there have been experiments recently that have shown this, that have actually shown that you can do work on an object. In this case, it was sort of raising up a tiny little particle that was sort of floating about in a liquid, if I remember rightly, by making observations on it, gathering information about its movements, and using that in some clever way. You can actually do work, raise it up against gravity. So information becomes a resource. So, again, there's this fundamental idea, and then the quantum version of it, which I won't go into, is just sort of enacting that same idea in terms of quantum information. So it's really interesting how, yet again, so many ideas, fundamental ideas in physics, but we also see it happening, of course, in biology, are coming down to this question of what information is, how it is embodied, how it can be used and manipulated, and how it can become a resource that we can exploit.
Thank you, Phil. That's wonderful. I see that we have a few more questions. I won't be able to get to all of them since I see we're about 15 minutes over, but perhaps let's take one more final question from Pranav here. If, of course, Phil, you would be happy to share with us on, how did you decide to go into physics? And then if you could tell us a little bit about your transition into becoming a science writer and an editor. I think it seems like there's interest from the audience if you'd like to share with us.
Well, talk about random walks. I mean, this was certainly one of them, because I began, my first degree was in chemistry, and it was at Oxford, where the final year you have to do a research year, which was fantastic. It was by far my favorite part of the course, and I did it on in physical chemistry on actually the quantum mechanical behavior of molecules absorbed on surfaces, which is right at the sort of borderline, really, of physics and chemistry. And so when I came to do a PhD, it just so happened that I ended up in a physics department looking at similar stuff, condensed matter and behavior of objects and fluids at surfaces. And so that brought me into physics. But I figured at the end of that, this was going back a long way, I can tell you, that unlike most people, I'd actually enjoyed writing up my thesis, and I enjoyed writing the papers that came out of this, out of the PhD. And so I thought, well, I'd never thought about this before. I'd always enjoyed writing, but I'd never thought about combining my enjoyment of writing with science. But you can. And I decided I'd see if I could do that in science editing. And I was very lucky that just at the right moment, a place came up at Nature, which in those days, this was the late 1980s, was just a journal. It wasn't this big publishing empire. It was just a single journal in a little office, a crammed office, piled with paper. And I got a job there as an editor of physical sciences, and had stayed there for a long time. It was a fantastic place to work. It meant I got exposed to all areas of science. It was a very, very steep learning curve. And it also opened up other opportunities to do writing for newspapers and so on. And eventually I decided maybe I'll write a book. And I did. And it was an awful experience in the sense that I was working full time at Nature, which was already, working. It was already an intense job. So I figured I don't want to do that again, but I want to write more. And I gradually became more and more part-time at Nature until I finally stepped down. I forget when it was, but it was probably about 20 years ago now. I stepped away from Nature. And I'd still write for them regularly as a freelancer, but I became completely freelance. And now I split my time writing, I guess, pretty much 50-50 between writing books, generally on scientific subjects, often about how science interacts with the rest of with the wider culture, and writing scientific journalism.
Thank you, Phil. That's it's an inspiring story. I think with that, I'll take maybe any final words you'd like to share with us before we thank the audience and yourself for joining us here today.
Well, just to thank you again, Zlatko, for inviting me to give this talk. It was great fun. It's always been a lot of fun having any interactions with IBM generally, and with the IBM quantum computing efforts in particular. So it's very nice to be able to sustain that relationship. And, I'm always fascinated to see where quantum computing at IBM and quantum technologies at IBM have advanced to next. So keep me in the loop about that.
Wonderful. And I think we all look forward to reading many more books and articles from you, Phil. This was an absolute delight. Thank you, everyone, for tuning in today. I still see we have over 130 folks tuned in, 20 minutes overtime. So I appreciate your time. Thank you very much. This talk will stay recorded and live on the Qiskit YouTube channel, so feel free to subscribe to hear about future updates. Thank you, Phil, for taking our invitation. It has been a real privilege and pleasure to have you here today. And thank you, everyone. We will see you next Friday at noon Eastern Time.
Thank you.